Hello my dear friends, welcome to IMS Academy. I hope that you people are doing well and you are sincerely focusing GATE 2025, and in respect to that, you know that fundamental, the foundation courses are being running on. Now today is the fourth session for the subject strength of materials, and already very neatfully 3 sessions we have conducted. So hello Atul. Yes. So 3 sessions we have conducted, and we have discussed the basics of 3 different topics, and today, although we have slightly delayed the session by 30 minutes, but no need to worry, we are going to learn the fundamentals of another new topic. And let me tell you that this topic is one of the most important topics as far as your GATE is concerned. So even if you are not able to attend it live, do make sure that you attend it in any time whenever you are free, but do attend it because this is very much important, and as from the name itself you can see that why this topic is that much important. It is stress transformation. Yes. So good evening Thiru, I hope the audio and video is clear. So the name of this topic is stress transformation, right? And you know my dear friends that the concept of principal stresses, principal strain are so much important, my dear friends, right? So let us try to today I'll be giving you the basics, the very good basics of this chapter, and I'll make sure that after this, this number of sessions on stress transformation, you will be in a very comfortable position to attempt any questions based on this topic, right? So without wasting any time, let us quickly come to the main topic. Now my dear friends, see, generally the state of stress at one plane we know, and sometimes it is required to know the stresses on different planes, right? So then the concept of stress transformation comes into picture. But everything has started from this general state of stress, my dear friends. Everything. In the first lecture I have told you that when you cut a section at a single point, in general you will find this is the state of stress, right? So clearly if I ask you how many stresses, independent stresses you are seeing, so you will say that sir, there are 3 normal stress plus 3 shear stress. So if I ask you that independently how many stresses you are seeing on this cube, so you will say sir, 3 normal stress, that is sigma x, that means sigma xx, sigma yy and sigma zz you are seeing. And how many shear stresses you are seeing? You are seeing 3 shear stresses, my dear friends. So one in the xy plane, one in the yz plane, and one in the zx plane. And yesterday, that means the previous day, I have also talked about shear stress equilibrium. So what was shear stress equilibrium? Quickly I am showing you that suppose this is the 2D state of stress that we are talking about. So this is tau yx, this is tau xy. So something like this, something like this. So again this is one tau and this is one tau. So all these 4 stresses will be equal. All these 4 stresses will be equal. All these 4 stresses will be equal. That means ultimately this is also tau, this is also tau, this is also tau, this is also tau. Something like this we are talking about. So for one plane, for example xy, we have one tau. So for yz we will have another tau. For zx we will have another tau. So ultimately 3 shear stress and 3 normal stress. So in total there are 6 independent stresses. In total there are 6 independent stresses. But my dear friends, when we start analyzing our real life scenario, it has been found that if we can somehow simplify the 3D state of stress, and if we just ignore something, try to simplify something, that means what I am trying to say, that I am talking about the planar state of stress, and what we generally say plane stress. So what is the logic? Logic is that suppose there are three principal stresses that you are seeing: sigma x, sigma x, sigma y, and sigma z, three normal stresses. And somehow if I design the material in such a way, or our materials are designed in such a way that normal stress or stresses in one direction is completely zero or negligible, then that type of stress is called as planar stress or plane stress condition. That means stresses in one direction is completely zero. For example, the stress associated with one direction, principal direction, is zero. Three principal directions I have: x, y, and z. So stresses, if we design the materials in such a way, or if the loads are subjected in such a way that stresses in one principal direction is completely zero. Now it may be due to design, that I have designed a very thin plate. So that condition is known as plane stress condition. And let me show you, my dear friends, that I am talking about this condition. Now can you see the difference between the previous figure and this figure? So previously you are seeing that, okay, this is x, this is y, and this is z. And in this figure you are only seeing x and y, my dear friends. You are only seeing x and y. Where is it? Where is it? In this direction you are seeing this is your z, this is your z. And now, so see, sigma z is there? Yes sir. Tau xz is there? Yes sir. So if I ask you that in one principal direction there are three stresses, one normal stress and two shear stress. And what is the changes that we are seeing in the plane stress? The stresses associated with z direction are zero, right? So this is called as what? Plane stress condition. Yes, Atul, 3D stress problems are in GATE. Just the basic problem, just the basic, when we designate 3D stress matrix. So questions related to 3D stress matrix can only be asked, but in general, most of the problems will be, 2D in nature. That means the plane stress conditions is only there in GATE syllabus, right? When we design 3D stress matrix, questions can be asked from 3D stress matrix, but in general, the complicated problems will not be there, right? So no, you can just, you can consider that in our scope only 2D or planar stress condition is there. Okay. Yes, so my dear friends, can you see the difference? That first of all, identifying difference is very important. That now I can only see in x direction and y direction, and in z direction stresses are zero. This condition is known as plane stress condition. Now if I ask you that now the stresses are acting on how many faces, what will you tell? The question is that now the stresses are acting in how many faces? Because later on I will show you a figure, later on, or you will identify a figure something like this. You will identify a figure something like this. So this figure you will encounter. This figure you will encounter later on. So what do you think? Am I talking about, if I ask you, am I talking about only one plane like this? Are we talking about only one plane or one face? How does this figure came into picture? From this figure to this figure, how did it come into picture? So now it will be clear that if I ask you in how many faces are you able to visualize the stresses, so you will say that sir, one, just a minute, you will say sir, on one face it is there, on second face it is there, again back side, this one, third face, back side, third face it is there, and left hand side, fourth face it is there. So on four faces there will be normal stresses and there will be shear stresses, and this is very convenient to express in this way. That is why from here to here the transformations have been made. So for example, if I have to represent sigma x, for example 1 and 3, so how will I say? This is your sigma x and this is your sigma x. 1 and 3 done. Shear stress on both 1 and 3, you can see both 1 and 3 face you can see. So sigma I have drawn, you can clearly see that this is your sigma and this is your tau, and this is your tau. Again 2 and 4, you can see two stresses. So this is your sigma y and this is your sigma y. And on sigma y there is again one shear stress on this face, and one on phase 2 one shear stress, on phase 4 one shear stress. So this is your tau over here and this is your tau over here. So whatever stresses are shown over here, this is very easily convenient shown in this 2D diagram. Now I hope that things are at least pretty much clear, that how from this to this we have gotten. So this is called as plane stress condition. The condition that you are seeing right now is known as plane stress condition. This figure when you see, this is called plane stress condition. But you know that how, if you have to visualize this figure, that how to visualize. So now you can visualize this 3D figure, and okay, and you can see that okay, this is somewhat the condition. I hope this much is clear. This much is clear. Now what is the objective over here? I hope the transformation from 3D stress condition to planar stress condition, what are the differences? This I have tried to explain you. So what is the objective over here? Objective is that I will be knowing sigma x, sigma y and tau for any, at any point. The question will be that at a different orientation, what will be the stress condition or plane stress condition? This is my objective. Now my dear friends, very important to know that I am talking about plane stress condition. If I talk about plane stress condition, so automatically you will be required to find out sigma x, sigma y and tau. If I ask you that find stress on a single plane, on a single face, if I ask you if on a single face, only one normal stress and one shear stress will be there. For example, see face number 1. If I ask you how many stresses you are seeing, you will say sir, 2 stresses, one is normal, one is shear. If I ask you on phase 2, how many stresses you are seeing, so you will say sir, on this phase I am seeing 2 stresses, one normal, one shear. If I ask you on phase 3, how many stresses you are seeing, sir, I am 2 stresses, and on phase 4 2 stresses. So on every phase there will be 2 stresses in plane stress condition, and right. And now when I give you this figure, and if I ask you that now I am shifting the orientation, I am changing the orientation, that means I am rotating this orientation by some angle, let's say 30 degree. So you can assume that this is the cube and somehow it is rotated by 30 degree. So then at that point you will be required to find that what is the plane stress condition. That means sigma x, sigma y dash and tau xy will be required to find out. This thing you people are able to understand? This thing you people are able to understand? So for example, this is the figure that you are seeing, that this is the 2D planar stress condition, and which I have explained to you. So automatically, if I ask you how many independent stresses are there, so you will be saying 3, sigma x, sigma y and tau. Tau will be same for everything. Okay. And this diagram or that planar stress condition, when it is shifted by theta, now you can clearly see that this theta is there with respect to horizontal, at least in this figure, and when it is shifted by theta, so when it is shifting by theta orientation, you are changing, and on that orientation again there will be 3 new stresses. Sigma x dash perpendicular to the face of sigma x dash, sigma y dash will be there. For example, if this is one plane stress condition, and how many stresses you are seeing? Sigma x, sigma y, tau xy. So if I change the orientation of this plane stress condition, sorry, if I change the orientation of this plane stress condition, that means in this way, so that means sigma x will be changed to sigma x dash. Wherever sigma y was there, now sigma y dash has come, and wherever tau xy has come, tau xy dash has come into picture. That means 3 different unknowns are there, and that is our requirement to find out. That is, we want to find out. Now my dear friends, how should we do that? How should we do that? This is the question. How should we do that? Okay. How should we do it? How should we do it? Okay. So clearly, my dear friends, you can see over here that this is my sigma x, or I can say the x direction. This is my x direction, and y direction will also be there. So from x direction, theta angle has been, it has been rotated by theta angle, and sigma x dash has come into picture. So here I have to draw one section. 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 Okay, here I have to draw one section. So just see the difference, that this is one figure and it has been raised by theta. It has been just tilted. I hope you are able to see the direction of rotation. It has been tilted by theta. It has been tilted by theta. So if you see over here, it has been tilted by theta. That means it is, theta. So something like this, entire thing has been shifted in the anti-clockwise direction as far as this figure is concerned. So this was your original, your original thing, and then the orientation has been changed by angle theta. So if you draw one section over here, for example, if I draw one section, so this was your original and now it has been shifted. That means the red one, 1, 2 was the original, and 1, 2 dash, that means there is a change with respect to theta. This is the theta, it has been shifted. So that means I have drawn one section over here, and this figure now is being shown in this way. This figure is now being shown in this way. So this was the original, and then this is. Now on this face only, there will be coming sigma x dash. Perpendicular to this face will be sigma y dash. Okay. So what we will do, my dear friends, we will try to take some area. We will assume that on this face, that is the x dash, that means I am representing by x dash on this face, that is this one, sigma x dash is acting and its area is delta A. So this is theta. So by method of projections, can we find out that this will be delta A cos theta and this will be delta A sin theta? We can very easily find out. This will be delta A cos theta and this will be delta A sin theta. Area we can easily find out. Now What is my purpose, my dear friends? Clearly see what is my purpose. If you see this figure, sigma x dash I want to find out and tau x dash I want to find out. This is my intention. So I have taken the area and I have named it. Now I will be seeing that what all are the forces which are acting on this respective faces. And after I identify the forces, after I know the forces, I will be using the method of equilibrium. That means I will be using the static equilibrium condition, and then I will be getting the value of sigma x dash and sigma y dash. Is it clear? Right now I have not given you any equations, my dear friends. Have I given you any equations of stress transformation? No. We will develop that, but after some time. Now simply on the basis of force equilibrium we are trying to analyze the figure, that how it is actually developing, how it is coming into existence. Okay. Now my dear friends, see this, I told you that this is area, this is what is the what is the area of this phase, that is sigma delta A. So what will be the force? Sigma x dash was the stress, so sigma x dash into delta A is the force on this phase. Obviously I told you that on a particular phase one normal will be there, one tau will also come. So tau x dash y dash, and if I talk about the force, you just simply multiply by area. That means if I will tell you the stress, and if you want to get the force, simply multiply by the respective area. For example, if I tell you that there is some stress on this face, that means this one. Now obviously you are seeing here as a line, but I have shown you how that earlier this was a face. Just for simplicity, how we are representing this we have understood. So see one thing, suppose you know the stress, whatever stress be acting, but if you want to get the force, simply multiply the respective area. For example, delta A is the area of the inclined line. For this horizontal, delta A sin theta was the area, so you multiply by that. Similarly for this one, the vertical one, delta A cos theta is the area. That means if you know the stress, you multiply by force, and simply, my dear friends, you have been in engineering mechanics, you have been doing force equilibrium questions like anything. You have done many force equilibrium questions. So simply we have to take the summation of the forces in a particular direction to be 0, and then we will get the answer. Simply we have to do this thing. So for example, see on this phase, now see this one, this phase, if I talk about this phase, so sigma x was there and tau xy was there, yes or no? Tau xy was there. So this is the phase, na, this phase, this vertical phase. So if you go back, so clearly you can see that on this phase sigma x is there, yes sir, tau xy is there, yes sir, and if I multiply with the area I will get the force, that is no issues. Okay, again I am showing you, for example, on this phase, on this phase, the bottom one, because bottom one is there, this is the triangle that we are dissecting now. So on the bottom one, what was the force? Sigma y was the force, from here you can see, and one shear stress tau was there. So in the new figure it must be there. So in the new figure, clearly what you are saying, sigma y is there, yes sir, and if you multiply with the area you will be getting the force. Similarly tau was there, you multiply with the area, you get the force. So just see what are your phases and simply multiply with the area, you will get the force, and ultimately we have to do only force equilibrium itself, simply force equilibrium, and we will get the answer. So no matter how many times I show you the figure and I keep on shouting, you will not understand with that much clarity until and unless I take a problem. So now what I will do, I will take a problem and then I will show you how to do it, how to apply the force of equilibrium. And if that question is clear, so then you will be knowing it very easily that how to apply what is the concept of stress transformation. If I take a problem, then you will be able to understand very clearly that how to do stress transformation. So please see this figure once. We'll discuss this question. Okay. So for example, assume that this is the train compartment and you are doing a journey in this train. One element on the surface of this train, assuming it's a plane stress condition, one element I have taken, and this is the stress distribution or stress components that has been shown that okay on this face. At least now you will not be confused or surprised that how this picture has come into existence in the first place, because you have seen that earlier it was a 3D stress condition, then two equal faces पे z direction all the forces have been taken as 0, and how they have been converted to only forces of x and y only. Now you will have no problem. So this is the state of stress, planar stress condition. Why planar stress? Because z direction forces are completely 0. Z direction forces are completely 0. Okay. Although it is not mentioned over here that which plane it is, but just for the sake of simplification I am considering it xy. Okay. The question is that he is asking you the forces on an element which is rotated by 30 degree from this base. Or if I want to show you, he is talking about something like this, that if this element is rotated by 30 degree, if this element is rotated by 30 degree, so this is the element, and just try to rotate by 30 degree. So you will get this figure. You will get this figure. Earlier this was the base. Earlier this was the base. Earlier this was the base, and from the base it is rotated by 30 degree. So tell me one thing, earlier if I ask you in the main figure how many stresses you are seeing, so you say 3 stresses, 180, 150 and one shear stress 25. And we know also that in a plane stress condition how many stresses we see? 3 stresses we see. If I ask you on how many faces they are being applied, 4 faces. How? I have already discussed. So if he is asking you about the new plane stress condition, the question is find the new plane stress condition. Earlier this was the plane stress condition, or plane stress when I say, it means I am talking about 3 stresses, sigma x, sigma y and tau xy in that plane. So question is, this is the initial plane stress condition given. If 30 degree, now as of now we don't have any equations. As of now we don't have any equations. We will have to solve anyway by the help of force equilibrium only. This is the only way I can say now. Later on, maybe tomorrow, I will show you that how equations are being developed. But as of now we have to solve by force equilibrium only. Are you getting or not? So, so tell me one thing. See this line, okay, see this line. Whatever I am drawing, just focus over here. I will be cutting a section like this, that is fine. But if I have to find the stresses in this way, that is the sigma x dash, so on this face definitely there will be one shear stress also. Let us say tau x dash y dash. So this stress can I show in this way, that okay on this face sigma x dash must be acting. Just try to match with this one. Just try to match with this one. Okay, ऐसा है sigma x dash, and definitely on this face tau is also there. So two things we have to find out. Okay. Now, sir, you told that, sir, sigma y dash will also come. Yes, sigma y dash will also come, which will be perpendicular to this face, sigma x dash. But we will see later on. We will see later on. But as of now, let's focus on one face only. One face per, we are trying to find one normal stress, that is sigma x dash, and the shear stress that comes, that is tau xy dash. This thing we are trying to find out. So ye figure dekho. Okay. Now if I ask you, on this face any force is acting. So yes, you will say that, okay sir, is face pe 80 is there. If I ask you that this face pe, since you have taken this one also, so this face pe koi force, any force you are able to see, so you say sir 50 is there, so 50 will be here also, and tau is there, and tau is here, and tau is there. Tau is on this face, tau is on this face. This thing, when I take it out, this thing when I take it out, you know, so when I take it out, so let me draw it again. So what was the thing? So now that triangle you have observed, So this is the triangle that we are talking about. On this face there is sigma x dash. On this face there is sigma x dash. This was the horizontal line earlier. Okay. Let's say this is your x. And over here some 50 is acting. There is 25 in this direction, and on this face 80 is there, and over here in the vertical direction 25 shear stress is there, and sigma x dash is there in this direction, and tau x dash y dash is there, you know, in the plane of the figure. And clearly, what is the angle change between, you know, sigma x dash and tau y dash, x dash y dash? So it is 90 degree. So once we have to apply the force equilibrium, in the sigma x dash direction, and once we have to apply the force equilibrium in the y dash direction, because this direction, if I talk about the new coordinate system, this direction is x dash and this direction is y dash. So two force equilibrium equations we have to use, one in the x dash and one in the y dash. Okay. So let us talk now about the x dash direction. Forces, acha, what about the area? So for example, you know that this angle is what? 30 degree. This angle is what? 30 degree. Okay. Now area is fine. Area, if this is delta A, so that this one will be delta A sin 30, and this one will be delta A cos 30. Okay. Area is fine. So see, this is the last time I am writing area. If I simply talk about stress, you multiply by area, you get the force. No need to see anything. For getting the force, simply multiply by area, you will get the force. Now the thing is that you have to take the stress equilibrium or force equilibrium in x dash direction. So what is the angle? Angle is, now see, this is 30 degree. So I can say by alternate angles, this is 30 degree, alternate angles. So this will be 60 degree because 90 a total. So this will be 60 degree. Yes or no? So see one thing, my dear friends, I am trying to show you that this is your direction of sigma x dash or x dash. This is your x. This is your 60-degree angle. Now some forces are there in this way and some forces are there in this way and some forces, you know, this is also one direction. Okay. Now see my dear friends, in the upper direction 25 is there. So I'll be writing here 25. See how I am doing. In the below direction directly, you know, in this direction there is 50 over there. So 50 will be coming something like this. Now in the, you know, x direction, in the x direction 25 is there and 80 is there. So in the positive x direction, in the x direction 25 is there, which is the shear stress, and 80 is there, which is the normal stress. This, now whatever forces I have, it was over here, I have shifted on this. 4 forces were there na, 1, 80, 25, 50, 25. So 80, 25, 50, 25. The angle between this is 30. And what we have to do? We have to simply take the force component in x dash direction and summation, means if I have to do what I have to do, summation fx dash is 0. Only this thing we have to apply. Only this thing we have to apply. Only this thing you have to apply. Okay. So x dash direction mein x dash, acha, stress I have written, mind it, I have written only the stress. I have written only the stress. So for force what I have to find out? Area se multiply kar do. For force what I have to do? Just multiply with the area, get the answer. And just you have to see that the stress is lying on which plane area. What is the area corresponding? For example, if I ask you this 80 compressive stress is acting on which area? So you will say, sir, delta is sin 30. If I ask you this 50 tensile is acting on which area? So delta is cos 30. If I ask you this 25 shear stress is acting on which area? Delta is cos 30. This shear stress is acting on which area? Delta is sin 30. Done. And its component you have to take in sigma x direction. That's it. That's it. That's it. So now I'm starting to know sigma x dash. Sigma x dash. Sigma x dash. But we have to write force, so multiply by area. What is the area of sigma x dash? Delta A. Delta A. Done. Now let's come on to this 25 and 80. 25 and 80 are very easy to take. Okay. Acha, it is in positive. It is in positive. Okay. So plus 25, but it is the shear stress. Now in ye jo shear stress, this shear stress, this 25, acting on which area? Acting on which area? So delta A cos 30 degree. This is the force. But we have to take in x dash direction. So cos 60 karna padega na. We have to do cos 60 because you have to take in that direction. Okay, done. 80. 80 is the compressive stress. 80 is the compressive stress. Okay. It is acting on which area? Delta is sin 30. Delta is sin 30. Acha, I have to take the component. I have to take the component. So cos 60. Do cos 60. So sigma x dash is done. 25, 80, done. Now this 50. Now this 50. Now see, if I extend this sigma x dash line in this way, to 50, and the angle between it is what? This is 90, this is 30, this is 30 degree. So what I can write? To minus, because it is minus, it is in the minus direction, to sigma x dash. 50, it is acting on which area? Which area? Sigma delta A cos 30. Area ho gaya, but you have to take the component cos 30. This 50 is also done. This 50 is also done. This 25 done. This 80 done. This 50. All this, only 125 is left, which is in the vertical direction. So plus 25. It is acting on which area? Delta is sin 30. Delta A sin 30. But you have to take the component this way. So cos 30. Cos 30. All the forces I have written. All the forces I have written. Very neatly all the forces are written equal to 0. equal to 0. And if you see, delta is there, delta A is there in all the terms, so delta A will be cancelled. Delta A will be cancelled, cos value very easily you will be able to take. So only one unknown is there, that is sigma x dash. Only one unknown is there, that is sigma x dash. And my dear friends, I am not going to solve it right here, I have already got the value. If you solve this completely, the sigma x dash value that you will get, it will be minus 4.5, minus 4.15, minus 4.15 megapascal, sigma x dash. So if you ask me that, sir, here you have taken the nature to be tensilic, that how it is coming out to be negative, that means the assumed direction is wrong, it must be compressive in nature. That means it is not acting like this, it is acting in the opposite direction. I hope this thing you people are able to understand. Please check once. I hope this thing you people are able to understand. I hope this thing you people are able to understand. Okay. Now on one phase, sigma x dash we have already found, but tau x dash y dash, that is left. That is left. Tau x dash y dash is left. So see, should I do it over here? No, no space is there. Can we do it? No, I'll draw it again, no issues, else you will get confused, So I'm drawing it again, don't worry. So again the base figure I am drawing, this is the base figure that I am drawing. So obviously I remember something, so this is 50, this was 50, this was 25, this was 80, this was 25. Now this is your tau x dash y dash. Perpendicular to it, what was perpendicular to it? Sigma x dash, normal stress. And you know that this is your x dash direction, x direction. And what was the angle? Angle was 60 degree. Yes or no? This one we have already found out. Yes or no? So once I have already taken the in the x dash direction, now I have to take in the y dash direction. So let me draw it the figure again. Let me draw the figure. This is your x, this is your x dash, this is our normal, the x, and this is the y1. y dash, x dash. The angle between x and x dash was 60 degree, and this is normal to this, that is the y dash. This is the y dash direction. See, this is the y dash direction. So this is 60 degree, this is 90 degree. So that means this one is 30 degree. Yes or no? And all the given components I am drawing, that is 20. Now what was the, and let me change the color. Okay. So over in this direction there was 125, comma there is 180. In the below direction there was 150, and above something like this there was your 25. And all the force components you have to take in y dash. All the force component you have to take in y dash. Simple. All the force component you have to take in y dash. If this thing you people are able to understand, then it's job done. Area you already know. So let us quickly do it. Okay. In this direction, what is the force? Tau x dash y dash. What is the area? Delta A. Now area already I have told you that this is your delta A. This was your 30 degree. So this area is delta A cos 30 and this area is delta A sin 30. Okay, tau x dash done. Now this 25, very easy to find out. This 25 shear plus 25, it is acting on which area? Acting on which area? Delta A sin 30 degree. Take the component cos 60, very easy, cos 60. Okay, now what is left? Now I think we have to draw in this way also, then only it will be clear. Okay, this is your y dash. Now one thing I am able to see, that whatever the remaining forces are there, I have to take in direction of y dash. I have to take the component in direction of y dash, so it will be minus. That sign will be minus. This thing I am able to see from here only. Okay, so minus. Let's take the shear 25. This 25. So it is acting on which area? Delta A cos 30. And what is the component? So you have to take in direction of y dash. So this is 30. So this angle, this is this. So this angle is also 30. Yes or no? This angle is also 30. So minus 20. So cos 30 done. So this 25 I have taken. Both the 25 I have taken. Now what is left? 50 and 80. This 50 and 80 is left. Okay, very good, no issues. So 50 negative. Minus 50 is acting on which area? Delta A cos 30. But you have to take the component in this direction. So this is 30 degree. So definitely this will be 60 degree. Cos 60 kar lo. Cos 60. Okay, 50 bhi ho gaya. This 50 is also done. This 50 is also done. Only one thing is left, 80. Okay, 80. So minus 80. It is acting on which area? Delta A sin 30. And take the angle cos. This angle 30 cos 30. Any more forces are there? No. Equal to 0. Done. So if you delta A present in all the terms, gone. Only one unknown, tau x dash y dash. And if you solve this, you will be getting 68.8 MPa. So on this phase, I told you on a particular phase, one normal, one shear will be there, and this value I have found out. Mind it, I have not used a single stress transformation equation. I have not used anything. I have only applied force equilibrium. That means one thing you people are able to understand, that the basis or the origin of developing the stress transformation equations is force equilibrium only. In one direction, earlier you had xy Cartesian system. When you rotate by some angle, it will be x dash y dash. Earlier you had sigma x sigma y. Now you will be having sigma x dash sigma y dash. What are all these things? I have explained you. So in this case, earlier you had what? xy. You rotated by some angle 30 degree. So now came into picture x dash and y dash. So x dash is corresponding to one face, y dash is corresponding to another face. On every face there will be one normal and one shear. X dash is corresponding to one face, y dash is corresponding to another face. And on every face there will be one normal, one shear. So right now whatever I have found out corresponding to one face, that is sigma x dash, and corresponding to in sigma x dash, which is corresponding to one face, there is one normal, one shear, and that only I have found out, one normal and one shear. So that means That means till now I have not found out sigma y dash. For that I have to section the material in a different way. Again force equilibrium I have to apply. And there will be, you will say that sir, there will be tau also corresponding to y dash. But I can say that tau will be equal to this only, because you know that in a particular plane stress condition there is only one tau, stress equilibrium. So only one unknown, sigma y dash will be left. But already you can see that how difficult it is to apply the equations every time and get the answer. So that is why we have developed stress transformation equations, but the origin is same only. We have to section one and we have to take the force components in every direction. So tomorrow, basics you have known. Tomorrow I will straight away, I will write here the stress transformation equations, and we will see that how to use that equations. And once we write the general stress transformation equations na, so you will be saying, acha, see one thing, planes are, it feels like one orientation is there and on different orientations can be obtained. So there might be some orientation on which there will be a maximum value of normal stress and a minimum value of normal stress, which is known as principal stress conditions. So all those things we will be seeing ultimately with the upcoming classes, but tomorrow we will again continue from here, that is the general stress transformation equations. Till now today we have not used any single equations, we have only used force equilibrium. So right, so here I will be ending the class, and tomorrow let us continue from here. Classes timing will be 4 to 5 only. In case of any emergency you can just, it might be shifted half an hour, something like that. So I hope you are enjoying the classes. Please leave your valuable feedback and comments in the comment section, and in case of any genuine doubt you can please drop your doubts in the comment section. I will be handling it, I will be replying to you. And if you are finding it useful, do like, share it with your friends. It might help someone, even if he or she is not preparing for GATE examination. The concept on the basics of SOM will be, you will be able to understand in a very clear way. At least this is my objective while teaching you over here, right? So till then, stay blessed, take care. Tomorrow let us meet us again, right? God bless.